Hi everyone. Today's topic, I am going to demonstrate a beat recognition system and a music beat recognition system. So you will be shown a demo of this beat recognition system, and I will be playing a animation which goes in synchronization with this particular system, so that you know, okay, yes, a beat is recognized. And of course, it's completely developed in Python, and I'll give you some tips on how you can make your own version, or how you can extend your own. And for all those who haven't done any signal processing, or if you even haven't heard of signal processing, this talk will serve as just a very basic introduction on how you can do some simple audio signal processing tasks in Python. And yes, I will be showing you those modules. So the outline of the talk is like this. There are a lot of demos, but before we start off with the demos, and I mean, some of the demos have some commercial outlooks as well. So it's not just research or something which you do for writing papers. It is something which can be very successful in the marketplace as well. So anyway, let us start with a few basics, so that a few basics of sound in general. It's now any sound that you hear, be it a digital sound or an analog sound, which means any sound which you hear in your life, will always have four characteristics. The first one is duration. I mean, how long is the sound? Does it last for 4 minutes, 5 minutes, 2 milliseconds? The second characteristic is pitch. Now, pitch refers to, in scientific terms, it refers to the frequency. It is analogous to the frequency of sound. Now, for the common man, pitch means when you ask someone to sing in a higher pitch, they raise their voice, like lower pitch would be so that is pitch. It corresponds to frequency, and it's measured in hertz. And humans can hear only between 20 and 20,000 hertz. So, of course, it's not a set range. You do have superhumans. The third characteristic is amplitude. Amplitude is nothing but how loud a sound is. The louder the sound, the greater the amplitude, or converse, the greater the amplitude, the louder the sound. And finally, we have something called timbre. Now, timbre is all the three previous characteristics. Duration you can measure, pitch you can measure, amplitude you can measure, but timbre is that aspect of sound which is very enigmatic, because timbre is the quality of music. It's the quality of sound, which means how is my voice different from your voice or your voice. Timbre is what is different. I mean, we can have the same loudness, the same duration, and the same pitch, and yet our voices will sound different. That's why, and that quality is called timbre. And okay, so this is all you need to know about sound. Any sound that you hear will have these four characteristics. So now, beat recognition. Now, this is my definition of a beat. It's a rhythmic pulse of music characterized by a repetitive, recognizable pattern, etc. What I mean by beat is, I mean, you would have heard club music or rap, hip hop. Any music has got a beat. If you've heard the bass drum going on in a techno or electronic song, something like doop, 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 that's beat. This is what I am assuming by beat. So I am going to show you a demo of this software which can recognize that beat in a song, and it will render a visualization where you will be able to see with your eyes that, okay, a beat is recognized. Now, why visualization? Because usually when more of your senses are able to confirm the same stimuli, that's when it makes it more immersive. By that I mean when your eyes and your ears confirm that a beat is recognized, that's when you can say, aha, yes, a beat is recognized. So I will move on to the demo. Okay, so this is what the simulation looks like. It's an aquarium, underwater aquarium. These are these bunch of balls floating around, and now these balls respond to Newton's laws of physics, which is action, reaction, and momentum and inertia. Now the thing about these balls is, as you can see, they are just floating around. Now when I play some music, what will happen is these balls will detect the music, and how it will happen is when a beat is detected, this ball will move faster and it will grow bigger in size. When a beat is not detected, it will move slow and it will shrink. So you will be able to see when that happens. I will just play a song for you so you can see what's going on. And back to normal. So how many of you could see that, okay, there was a beat recognized? Okay, no one. Okay, someone, two people. So that's it. So
sorry, it actually looked like it was responding to the baseline.
Exactly, the baseline.
Yeah. Rather than the actual the drum beats. Was that it?
It responds to the by baseline you mean the drums?
The bass synthesizer.
It was meant to. Doop, 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 doop. Did you mean this or?
Yeah, I may have seen it wrongly.
Okay, so here's the thing about beat detection, and it's already been brought up, is that now we can all agree on when we hear a beat, but when we visualize it, when we see it, each of us expects to see something different. For example, what you may want to see while you're listening to techno music may be different from what I visualize when I listen to techno music. So the aim of this is to have a very generalized criterion. So that's why I've chosen club music, where there are just beats. So I'll just give you another example so that it's clearer. You know what? I'll just play it at 3/4 of the speed.
So it doesn't pick up like the cymbals, is it?
It doesn't pick up the cymbals. It picks up only the beat, the main percussion instrument beat, and that is one of the assumptions I've made, because the thing about picking up the cymbals is, apart from the complexity, it would an apt visualization would be difficult to configure for each and every person. So hence it just picks up the bass beat, the loudest drum beat you can hear. So that's about it. And
you run this, you're entering two parameters. One is its speed and one is quantization. So what is the second one? Is that the rate at which you're sampling?
that is how many samples I choose to process. Now that is for my own research purposes. So I will explain in the coming slides as to how I have used that. Okay, so now I have made some assumptions and to detect this beat. One is that a beat occurs every 0.3 to 0.7 seconds. Now that's reasonable to assume because I doubt modern music will have a beat which occurs less than 0.3 seconds. It would not sound very musical. And more than 0.7 seconds, while this software can of course detect beats more than 0.7 or less than 0.3, but usually sounds which have beats, by beats I mean the main beats, the drum beats, the loud bass beats which you can hear, falls between this range. And yes, and then the second is that the music which I've chosen is limited to instrumental club music. Now the modules I've used is the animation you saw was pygame, and for signal processing I've used something called PYO. It's not to be confused with the .pyo bytecode files in Python. So just a very basic. Now there are many ways to detect a beat, many ways. I mean you can do it in the time domain or you can do it in the frequency domain. There are a lot of ways people have done this. How I have done this is to choose a very simple method, is to detect the amplitudes. Now what is an amplitude? It is how loud the sound is. So the songs which I've chosen, the loudest sound is your bass drum. That has the largest amplitude. So I want to detect this bass drum as during the duration of the song. So what I do is, now this is a snapshot of 1 second of a song. You can see the time here and the amplitude here. Don't worry about these values, just see which is bigger and which is smaller. Now I take every 1,000 samples and I store them in a buffer. Now what are samples? Samples is nothing but individual pieces of audio data. Now 1 second of a song usually in modern music has 44,100 samples. So what I've done is I take 1,000 samples and I calculate its average, and I do this for the whole song. Every 1,000 samples I calculate the value and I store it. Now before the next method, why 1,000? 1,000 is empirically determined. You know the quantization value, that I chose that as 1. That was 1 into 1,000. If I chose 5, it would be 5,000. So, but I've got best results using just 1,000 samples. So why 1,000? It is completely trial and error. It is, in scientific terms, they call it empirically determined, to give it a more sciencey way, but it's just trial and error. Yes.
44,100 corresponds to CD?
Yes, yes. Usual sampling rate for MP3s. Now I have calculated the 1,000. I've calculated the values of every 1,000 samples, and I keep comparing them. Now what I do is when you compare these samples, my main aim is to find the sample which is the loudest, which has the maximum value within a 0.3 and 0.7 second window. Now whichever is the largest, that is the precise location of the center of the beat. So the moment I get that value, I assume that is the beat location. So which means I calculate this. I calculate all these values, and I realize that, okay, there's a major spike here. This has got to be the beat. So that's when I say that, okay, this part, a beat is detected. And then, of course, 1,000 samples is just 1,000 by 4,400, just 0.04 milliseconds. No beat is that short. So I take the values before it and after it and assume that as a beat. Now you just repeat this for the entire song, and you will be able to get the beats as determined by the loudest sound in the song. So the Python module used for this is PYO. You can just get it. It's there for Windows, Mac, OS X, and Linux. So you are able to do a lot of different kinds of signal processing using this module. Mathematical operations. You have your Fourier transforms. You can have synth gens, and of course it supports the MIDI protocol, which means you can even boot it on your cell phone or Raspberry Pi, and it'll just work great. So of course this is just theory.
What does it mean to create sound granulation?
To create sound granulation.
Algorithms to create sound granulation.
Well, that is when you want to mix a lot of different kind of sounds and play around with it. Like you see the console, I think that where you have many knobs. Yeah. So now I'm going to demo a simple sine wave generator. This is just very simple code. You import the module, you initialize, and you generate a sound wave. And this particular library lets you test it by giving you a very nifty GUI. So I'll just give you a very short demo. You can hear that. That's a sine wave at 1500 hertz. Now, I mentioned humans can hear only between 20 and 20,000 hertz. So, who can hear this?
Oh my God.
Can someone hear this?
Your amplifier on your laptop probably has rolled off higher than 20 hertz.
I guess, but and this, I'm sure all the dogs can hear this. This is at 20,000 hertz. So, yeah, so that's it, simple sine wave. Now, it may seem that this sort of thing doesn't have any commercial value. I mean, it's just a sine wave, but you have dog whistles, sonar, ultrasound, and there's another emerging use of this is sonic weapons. Now, sonic weapons were used by the American Navy in to ward off the Somali pirates. So the main, it's a growing field of research. It's known as a long-range acoustic device. So now when I play a sound here, everyone can hear this, but the theory behind acoustic weapons is to direct a beam of sound so loud at only one person, and it won't incapacitate you. You won't die of it, but there'll be a lot of pain, nausea, disorientation.
Can you get deaf from that?
Possibly, it can hamper your eardrums. And there were cases when one guy could hear a sine wave throughout his life. It never stopped for him. So, tinnitus, yeah. So let me just give you a demo of what an acoustic weapon would be like. That's it. We'll see who has the last laugh. So usually acoustic weapons, sonic weapons are designed like this, and a lot of presenters do this. Yeah, peace on earth. So now no one has ever died from the Python interpreter, but Pythons are poisonous; they can kill you. So now, since everyone can hear this, it's okay. But if it's directed like a laser, it can really harm you. So stay away. Okay. Okay. Now commercial applications. Has anyone heard of this app, the Talking Tom app? It had a lot of downloads, made the creators a lot of money. And it's something like this.
And you can also let him record your voice. So I'll go like this. Hello, how are you? Hello, how are you? You can also record it. Hello, hey, shut the hell up.
So the app it's just this interactive cat. You just speak into the microphone, and he replies with a very chipmunk-like voice. So I mean, it's a lot of fun to play around with. So now the main draw of this app was 50-50. Of course, the graphics were great, but then the most fun part was seeing your masculine voice getting all chipmunk-like. So this is not a very complex signal processing challenge. It can be achieved by something called time pitch modification, which is nothing but increasing the pitch of your voice, making it sound higher, and expanding the duration of the sound. Because usually when you speed up music, it gives you the chipmunk-like voice, but it's very fast. So what this does is it increases the pitch and doesn't change the duration or the tempo of the music. So it's just a simple app which I created, very basic. Hello? Hello, are you there? Okay, I don't think the mic works, so I'm going to use my speakers. Okay, now the audio is going to come from here. I hope you guys can hear it at the back. Hello? Hello? Hey. Hello? Hello? Oh, forgot this. USB speakers. Very used to wireless. Oh. Hello?
Hello?
Okay, that's feedback. Hello? Hello?
Hello?
Hi.
Hi.
How are you?
How are you?
So it gives you the same effect. It's very easy to prototype using Python. I know a lot of people here would probably be developing for many different platforms where you cannot directly upload a Python app, but you can really use Python to prototype these things and grab the science and just use it for your own platform. So this is one application, and is how you can work around with your sound. Another thing is, anyone's seen Iron Man, of course. So there's a robot in this, Jarvis. He sounds like a robot, right? So I tried to do something where I put my voice in, and the output is just a very robotic voice with no emotion, absolutely zero emotion. Hi. Hi.
Hi.
How are you?
How are you?
La la la.
La la la.
I don't know what's with that. La la. I mean, there's no change in his pitch. He is very he is very cold. So there's a lot of things possible with sound. I mean, and not just for scientific research. You can make a lot of applications with this. This is just a very, very small peek into how you do this. And other things possible are drum beat generators. I mean, there are many open source alternatives like Udacity, and you have GarageBand, which you can create music, but you can also do it in Python. Now, given these 4 sounds, 4 drum sounds, 3, 4. This is how Python creates music. Okay, so this is there's a feature in this library which allows you to which creates a beat class, and there's a beat function, and you can pass a set of 16 different numbers, binaries, ones and zeros, which means a hit. It means a hit and a hit without noise, and you can generate all sorts of melodies and sounds with that. You should check this out. Get this if you're running Python, just on any platform, just get this module, PYO. This will help you do all these cool signal processing things, and you can check out some of these. This is very nice, Scikits and PyAudio. And if you want to learn the theory behind DSP and audio signal processing, you should get this book, buy it from this link. So I think these slides will be published later. So yeah, you can get the links from there. And that's all for today. Thank you.
What are the dependencies on Pi? Is it completely standalone module?
Standard module, no dependencies.
It's like nothing like NumPy or anything behind?
Nope. It works on this MIDI protocol, so which means that it needs no dependencies as such.
So MIDI, if I recall correctly, MIDI is like a set of instructions to your sound card.
Exactly. That's it. That's all it is.
Right. So what it does is it sends an instruction of sine wave, pitch.
Yeah. It sends all that information, and the sound card will know how to play whatever it sends.
Is it possible to isolate frequencies and remove them?
It should be possible. It has functions for Fourier transforms, which will allow you to see the whole range of frequencies. Then you can cherry pick. You can use low pass, high pass, or band pass filters to just remove whatever sound you want.
And does it have a bit of visualization if you want to?
Yeah, it has. I think it's using WX Python for that.
Okay.
So you will need WX Python just for the visualization parts.
Does that create engineering that we process so you can actually play MIDI file with some other instruments?
Yeah, there is an option to save whatever you've played as a MIDI file, as AIF, WAV, or MIDI. So you can.
Is it possible for the computer to recognize the word that you type and generate a voice with emotion?
That sounds hard.
It's possible. Anything's possible. So it's up to you. You can just give it a try and buy this book. No, I haven't written it, but still buy this book. It's a great book. It's got a lot of ideas you can mix and match, and this will just tell you how to use audio, and you can do a lot of crazy things with it.
Are you aware anyone like musician or composer using Python to create? So
No known musicians. Not apart from the drum thing, nothing really as such. But I mainly like to rip apart the music files and just play around with them, introduce filters, see what it sounds like, but not for creating music. I guess if you want to create music, it's best to use just like GarageBand on Mac, or it's just easier.
I think there's a lot more tools in, I don't want to say the language, but there are a lot of other tools that allow you to do stuff like to bring music up, or yeah, I don't think there's such tools in Python yet, so that's why. They're not in, like, I mean, they're tools by themselves. For example, there's one thing called MaxMSP, which is probably written in C, I would think, which allows you to do a lot of these kind of synthesis or whatever, to make music in all weird ways. But it's you need tools because musicians don't want to start coding. They rather have user UX, like a lot of these tools tend to be drag and drop kind of stuff. So you drag and drop different elements and you connect them up and stuff. So yeah,
that's just easier instead of writing a script. Could give you more power though, but it's up to one of us to explore.
Last question? Anyone? Okay, if not, thank you, Vikram. This is a token of appreciation from the committee.
Thank you.
So,
Thanks, George.